Type sine of 37 degrees into any calculator, and in less time than it takes you to blink, it hands you 0.6018. Because inside that chip, there is no triangle. There is no protractor, no ruler, and no little unit circle spinning quietly in the silicon. The processor at the heart of your calculator can do exactly four things: add, subtract, multiply, and divide. That is the entire vocabulary, and every other function in mathematics has to be built out of those four words. So somewhere between pressing that button and seeing that number, sine has to be rebuilt out of plus, minus, times, and divide. The answer to how is one of the most beautiful ideas in all of calculus, and once you have seen it, you cannot unsee it. It says that almost every curve you can imagine is secretly a polynomial in disguise, an infinitely long one. It is called the Taylor series, and by the end of this video you are going to compute sine by hand, using nothing but arithmetic, and match your calculator digit for digit. If you enjoy watching mathematics get taken apart like this, subscribe. It genuinely helps the channel. Before we build anything, let's kill the obvious answer. Maybe the calculator simply stores a giant table of sine values and looks yours up. It is a reasonable guess, and it is very nearly what the oldest machines did, but it cannot be the whole story. Between 37 degrees and 38 degrees, there are infinitely many angles, and between any two of those, infinitely many more. No table, however large, can hold them all. You would need infinite memory inside a device that fits in your pocket. What the machine has instead is a recipe, a short, fixed list of arithmetic steps that works for every input you could ever type. And there is exactly one family of functions you can build from adding and multiplying alone: polynomials. A polynomial is nothing but numbers, powers, and plus signs, and a chip can evaluate one in a handful of clock cycles. So the real question sharpens into something much stranger. Can a polynomial, a thing made of straight-line arithmetic, actually become the sine wave? Let's try to build one, and let's be greedy about it. We will pick a single point to obsess over, the origin, x equals 0, and demand that our polynomial agree with sine there as completely as it possibly can. Agreement number 1, the height. Sine of 0 is 0, so our polynomial had better pass through the origin as well. That is one condition satisfied, and it has bought us almost nothing: a flat line that brushes the wave once and immediately abandons it. Agreement number 2, the slope. The derivative of sine is cosine, and cosine of 0 is 1. So at the origin, the sine wave rises at exactly 45 degrees. Make our polynomial simply p of x equals x, and now the two curves do not merely touch, they leave the origin traveling in the same direction. And look how good that already is. Sine of 0.1 is 0.09983. Physicists have quietly leaned on that approximation for 300 years. It is the entire reason a pendulum has a clean formula, provided you do not swing it too hard. But push further out, and the straight line escapes upward, while sine politely turns over. The line fails because it never bends, and bending has a name in calculus: the second derivative. So agreement number 3, the curvature. The second derivative of sine is minus sine, and at 0 that is 0, which means, surprisingly, sine has no bend at the origin at all. Our x squared term gets a coefficient of 0 and disappears before it is even born, which tells us something structural about sine. Near 0 it is not a parabola, it is something odder, and we will have to go one derivative deeper. The third derivative of sine is minus cosine, and at 0, that equals minus 1. So we want a cubic term that pulls our straight line downward, but by exactly how much? Here is where the factorials come from, and it is the single step most textbooks sprint past. Take the term c times x cubed and differentiate it 3 times. Each differentiation drags the exponent down in front, so you collect 3 times 2 times 1, 6, and 6 is 3 factorial. So the third derivative of that one term is 6c, and we needed it to equal -1. Therefore c is -1 over 6, or, written the way it wants to be written, -1 over 3 factorial. And that pattern is completely general. Differentiate x to the n exactly n times, and you always land on n factorial. Which means that if you want your polynomial's nth derivative to match the real functions, you must divide by n factorial to undo what differentiation piles up. Write that down, and you have the entire theory in a single line. The function, near 0, equals its value, plus its slope times x, plus its second derivative over 2 factorial times x squared, plus its third derivative over 3 factorial times x cubed, and onward forever. Each coefficient is a derivative at the center, divided by a factorial. The derivative supplies the information, and the factorial supplies the correction. Centered at 0 like this, it is called the Maclaurin series, after Colin Maclaurin, who set it out in his treatise of fluxions in 1742. Center it anywhere else at a point A, and you have the General Taylor series, named for Brooke Taylor, who wrote it down in 1715, 27 years earlier. And that center is a choice you make. Drag it along the curve, and the region of good agreement travels with it, like a bubble of accuracy you can move wherever you need it. Now let's turn the crank on sine and watch what falls out. Differentiate sine and you get cosine. Differentiate again and you get minus sine. Again, minus cosine, and once more you are back where you started. Sine's derivatives run in a loop of length 4, which guarantees its coefficients will run in a loop 2. Evaluate that loop at 0 and you get 0, 1, 0, -1, and then it repeats forever. Every even power dies, every odd power survives, and the signs alternate, exactly the odd symmetry we spotted earlier. Feed that into the formula, and the sine series appears. Sine of x equals x, minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, and on without end. Written out with the factorials worked through. X minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040. And before we go further, a small piece of justice. This series was discovered in Kerala in southern India by the mathematician Mahdi Hava around 1400, roughly 3 centuries before Taylor was born. Now watch what these terms actually do. Degree 1, a straight line honest near the origin, useless past it. Add the cubic term and the line bends over, it catches the first hill. Add the 5th power, and it follows sine all the way down through the 0 at pi and starts the descent. 7th, 9th, 11th, each new term extends the agreement outward, like a wave of loyalty spreading from the origin. By degree 15, the polynomial and the sine wave are indistinguishable from -5 to +5, comfortably more than a whole wave, and there is no daylight between them anywhere in that window. Push to degree 25, and it holds all the way out to plus and -9, nearly 3 complete waves from a polynomial. And then always, at the very edge, the polynomial gives up and hurls itself at infinity, because any polynomial of finite degree must eventually run off forever, while sine never does. Only the infinite series is truly sine. Every finite piece of it is a beautiful approximation with an expiry date printed on it. Let's go back and settle the question we opened with. Sine of 37 degrees, except the series only speaks radians, so we convert first. 37 degrees is 0.64577 radians, and that is the x we feed in. First term is x itself, 0.6458, already within 7% of the answer from a single multiplication. Subtract x cubed over 6, that is 0.04488, and we land on 0.60089. Add x to the fifth over 120, just 9/10,000ths, and we are at 0.60182. Subtract x to the seventh over 5,040, 9/millionths, barely a nudge, and we get 0.6018150. That is your calculator's answer, correct to 7 decimal places, from 4 terms and nothing but multiplying and dividing. 4 terms, that is the whole magic trick. But looks identical is not a proof, and no engineer ships an approximation they cannot put a bound on. So exactly how wrong is a truncated series? Taylor's theorem answers with startling precision. The error left over after the nth term is the very next derivative, evaluated at some unknown point between your center and your target, divided by n plus 1 factorial times x to the n plus 1. We usually have no idea where that mystery point c actually is, and remarkably, we do not need to. Because for sine, every derivative is a sine or a cosine, so whatever c turns out to be, that top term can never be bigger than 1. That hands us a hard ceiling. The error is at most x to the n plus 1, divided by n plus 1 factorial. And now look at the race between those two quantities. Powers grow fast, but factorials grow ludicrously faster. 20 factorial is already more than 2 quintillion. So for any fixed x, however large, the factorial eventually overtakes it and crushes the error to nothing. There is even a rule of thumb for when the crushing begins. You need roughly e times x terms, and yes, that is the same e turning up uninvited as it always does. That is why sine series converges for every real number you can name, and why 4 terms was plenty for 37 degrees. Sine is not special. Once you have the machinery, the great functions of mathematics fall open one after another. Take e to the x, the function that is its own derivative. Every derivative is e to the x, and at 0, every single one of them equals 1, so every coefficient is simply 1 over n factorial. The most self-referential function in mathematics has the tidiest series in mathematics. Cosine you can get for free, just by differentiating sine series one term at a time. 1 minus x squared over 2 plus x to the fourth over 24 minus x to the sixth over 720. Even powers only, which is exactly what you would demand from a curve that is symmetric about the vertical axis. The natural logarithm of 1 plus x gives an alternating series with no factorials in it at all. And the simplest of the lot, 1 over 1 minus x is just 1 plus x squared plus x cubed forever, the geometric series, which you can check without any calculus at all, by multiplying both sides by 1 minus x and watching the whole thing telescope into nothing. But this last one comes with a warning label, and that label is about to blow our entire story open. Put x equal to 2 into that geometric series. The left-hand side is 1 over 1 minus 2, a perfectly ordinary minus 1. The right-hand side is 1, plus 2, plus 4, plus 8, plus 16, marching off to infinity without a backward glance. The series here is not merely inaccurate, it is meaningless. It only works when x lies strictly between minus 1 and 1, and that interval has a name, the radius of convergence. For the geometric series, that is easy to swallow. The function itself blows up at x equals 1, so naturally the series quits there. But now consider 1 over 1 plus x squared. This curve is perfectly smooth and perfectly finite for every real number. It never blows up, never breaks, never so much as flinches. And yet its series also dies at exactly x equals 1, and nothing anywhere on the real line explains why. The explanation is not on the real line at all. It is hiding one dimension up. Up here, 1 over 1 plus x squared has two places where it detonates, at plus I and at minus I, because there, 1 plus x squared is exactly 0. And the distance from the origin out to each of them is exactly 1. So the radius of convergence is literally a radius, a disk around your center that grows until it strikes the nearest point where the function breaks, even when that point is invisible from where you happen to be standing. There is one more piece of honesty owed to you, and it is the strangest fact in the whole subject. Consider e to the minus 1 over x squared, defined to be 0 right at the origin. It is perfectly smooth. You may differentiate it as many times as you like forever, and it never complains. But every single one of those derivatives, evaluated at 0, comes out to 0. So its Maclaurin series is 0 plus 0x plus 0x squared, the 0 function which converges everywhere, to entirely the wrong answer. Having a Taylor series and being equal to your Taylor series are two different things. The functions where they agree are called analytic, and they are the well-behaved aristocracy of mathematics. So is the Taylor series, what is genuinely running inside your calculator. Almost but not quite, and the difference is worth knowing. A Taylor series spends all of its accuracy near the center and gets steadily worse as you travel outward, which is a strange way to budget if you care about the whole range equally. Engineers would rather spread the error out evenly, so they use cousins of the Taylor polynomial, mine max and Chebyshev approximations, tuned so that the worst error anywhere is as small as it can possibly be. They also cheat before they start, folding any angle you type down into a tiny window near 0 using sine's own symmetry, where a three-term polynomial is already accurate to the last bit the machine can store. And older pocket calculators used something different again, a shift-tandad method called ko-ardic, which rotates a vector through a fixed ladder of ever smaller angles until it lands on yours. But every one of these techniques stands on the foundation Taylor laid. Replace the impossible function with a polynomial and keep the error on a leash, and that idea escapes the calculator entirely. Because when a physicist says a pendulum has a fixed period, or when Einstein's kinetic energy collapses back into 1/2 mv squared at everyday speeds, or when an engineer says any smooth valley behaves like a spring near its bottom, all three of them are quietly throwing away Taylor terms too small to matter. So the next time your calculator answers before you have finished lifting your finger, remember what it is really doing. Not looking anything up, but adding a handful of numbers together, fast enough that infinity never gets the chance to complain. Thanks for watching.